It has to do with curiosity. It has to do with people wondering what makes something do something. And then to discover that if you try to get answers, that they're related to each other. That the things that make the wind make the waves, and the motion of water is like the motion of air, is like the motion of sand. The fact that things have common features turns out more and more universal. What we're looking for is how everything works, and how everything is, what makes everything work. But it's curiosity as to where we are, what we are. It's very much more exciting to discover we're on a ball, half of it sticking upside down. It's spinning around in space. It's a mysterious force which holds us on. It's going around a great big glob of gas that's burning fueled by a fire that's completely different than the fire, any fire we can make. Well, now we can make that fire, nuclear fire. No. But that's a much more exciting story to many people than the tales which other people used to make up who worried about the universe, that we were living on the back of a turtle or something like that. They were wonderful stories, but the truth is so much more remarkable. And so what's the pleasure in physics is that, to me, is that as it's revealed, the truth is so remarkable, so amazing. And I have this disease, and many other people who have studied far enough to begin to understand a little of how things work are fascinated by it. And this fascination drives them on to such an extent that they've been able to convince governments and so on to keep supporting them in this investigation that the race is making into its own environment. There are lots of things that people did. For example, Maxwell put the equations together. The Faraday formulated the equations mathematically with some model in his head. And then Dirac got his answer by just writing and guessing an equation. And other people got their answer, like in relativity, got the idea by looking at principles of symmetry. Now, all these methods, and Heisenberg got his quantum mechanics by thinking only talk about the things that you can measure. Now, all of these ideas, we should only talk about things that we can measure. Try to define things in terms of only things you can measure. Or let's formulate the equation mathematically. Or let's guess the equation. Or all these things are tried all the time. Look for symmetries. All that stuff is tried. All that stuff, when we're going against the problem, we do all that. That's very useful. But we all know that. That's what we learn in the physics classes, how to do that. But the new problem, where we're stuck because all those methods don't work. If any of those methods would have worked, we would have gone through there. So when we get stuck in a certain place, it's a place where history will not repeat herself. And that's makes it even more exciting, because whatever we're going to look at the method and the trick and the way it's going to look is going to be very different than anything that we've seen before, because we've used all the methods from before. Therefore, a thing like the history of the idea is an accident of how things actually happen. And if I want to turn the history around to try to get a new way of looking at it, it doesn't make any difference. I don't care. The only thing that the real test in physics is experiment, and history is fundamentally irrelevant. What today do we not consider part of physics, which may ultimately be part of physics?
I see.
And I realize immediately something. We consider, at the present moment, most people consider that we study the laws of physics, that is, how things go, given a certain condition, how the things behave after that. But how did they get into that condition is considered another problem. In other words,
boundary conditions.
Right, boundary conditions. We are given the conditions, the circumstances, and then it evolves from there according to physical laws. We're studying the laws.
Yeah.
It's as though we were doing a chess game again, and we're working on the rules, but we're not worrying about how the pieces are supposed to be set up on the board in the first place. That's not our business. That's the business of history, how the world evolved. Astronomical history of cosmology, how the universe exploded or the steady state or whatever it was. It's not our business. It's interesting that in many other sciences there's a historical question, like in geology. The question, how did the Earth evolve to the present condition? In biology, how did the various species evolve to get to be the way they are? But the one field which has not admitted any evolutionary question is physics. Here are the laws, we say. Here are the laws today. How did they get that way in time? We don't even think of it that way. We think of, well, that is that way from forever. It's always been like that, the same laws, and we try to explain the universe that way. So it might turn out that they're not the same all the time, and that there is a historical evolutionary question.
But how do you see it going? It's hard to speculate. Is it a continuous change, or is it something that depends on big
You're the
This
speculator,
great,
Steve. You and I
tragedy.
think differently. I think of the possibilities, but I'm afraid to put things in. When I see the dark, I always figure the dark as too big for me to guess at. You see, to guess, it's not much use in guessing particular things. But you're different, and I would like to discuss with you sometime how do you do that, because I'm really a little afraid to make specific
is
guesses.
Your background.
I don't
The
know.
way you kind of grow up.
I don't know. I'm afraid to make specific guesses because the moment I'm making that guess, I can see 7 other alternatives. And so, since I see these other alternatives, I don't know which one to piddle with.
Well,
I don't like to spend a lot of energy on one.
My choice is very simple. I don't set any requirement that the answer be right. It's just what I'm interested to follow.
That's the difference. That's the difference. That's the difference.
Yeah.
Well, I'm trying to find
If I'm
out.
interested in
I'm trying to find out not how nature could be, but how nature is. See how what's right.
Well, I don't
and
think
you're
you'll ever
interested-
find it, you see. I don't think
Right.
you'll ever find it.
I see. And your idea is to find out what nature could be. What different possibilities.
No,
different
what
possibilities.
I think is interesting. Yeah.
Even if it's wrong.
What you're looking at is a very large mass of atoms when you look at a particle that you can see, because a particle you can see even in the microscope is a billion atoms or so. It's a great big thing. But it doesn't stay put because it's being bombarded all this time by the little atoms, and it therefore jiggles a little bit, and that's called Brownian motion. It was discovered by Robert Brown, a biologist, that when he looked through a microscope, he saw this jiggling motion. And being a biologist, you would think that he would decide that this motion that he saw must be a form of life. But he was a good biologist and made the necessary experiments and ultimately discovered that the motion even existed in the water that was enclosed in a quartz crystal that you could get from the ground that had been there for millions and millions of years. And he looked in, it was still jiggling inside there, so he concluded that couldn't be life, that was a universal phenomenon of nature, and it is, that we look very calm, we look at things, they're permanent, they're stationary, but as a matter of fact, of course, they're made out of piles of atoms which are always jiggling. Our eyes can't see the delicate jiggling, but that is a way that you could make a random generator. You could amplify such jiggling. The electrons and wires jiggle too, everything's jiggling. This picture of atoms is a beautiful one that you can keep looking at all kinds of things this way. You see a little drop of water, a tiny drop, and the atoms attract each other. They like to be next to each other. They want as many partners as they can get. Now, the guys that are at the surface have only partners on one side here, in the air on the other side, so they're trying to get in. And you can imagine this team of people, these teeming people, all moving very fast, all trying to have as many partners as possible. And the guys at the edge are very unhappy and nervous, and they keep pounding in, trying to get in, and that makes it a tight ball instead of a flat. And that's what, surface tension, the way when you realize, when you see how sometimes a water drop sits like this on a table, then you start to imagine why it sits like that, because everybody's trying to get into the water. And at the same time, while all this is happening, there are these atoms that are leaving the surface, and the water drop is slowly disappearing. I find myself trying to imagine all kinds of things all the time, and I get a kick out of it, just like a runner gets a kick out of sweating. I get a kick out of thinking about these things. I can't stop. I mean, I could talk forever. If you cooled off the water so the jiggling is less and less, and it jiggles slower and slower, then the atoms get stuck in place. They like to be with their friend. There's a force of attraction, and they get packed together. They're not rolling over each other. They're in a nice pattern, like oranges in a crate, in a nice organized pattern, all just jiggling in place, but not having enough motion to get loose of their own place and to break the structure down. And that's what I'm describing as a solid. It's ice. It has a structure. If you held the atoms at one end in a certain position, all the rest are lined up in a position sticking out, and it's solid at the end. Whereas if you heat that harder, then they begin to get loose and roll all over each other, and that's the liquid. And if you heat that still harder, and they bounce harder, then they simply bounce apart from each other, and they're just individual, I say atoms, it's really little groups of atoms, molecules, which come flying and hit. And although they have a tendency to stick, they're moving too fast. Their hands don't grab, so to speak, as they pass, and they fly apart again. And this is the gas we call steam.
When I was a kid, I invented a problem for myself, the sum of the powers of the integers. And in trying to get the formula for it, I developed a certain set of numbers formula for which I couldn't get. And I discovered later that those were known as the Bernoulli numbers, and discovered in 1739. So I was up to 1739 when I was about 14, you see. And then a little later I discovered something. I find out they invented a thing called, which we now call operator calculus. And that was invented in 1890 something. You see, I was inventing things that came later and later. But the moment when I began to realize that I was now working on something new was when I read about quantum electrodynamics at the time, and I read a book and I learned about it. For example, I read Dirac's book, and he had these problems that nobody knew how to solve. They were described there. I couldn't understand the book very well because I really wasn't up to it. But there, in the last paragraph at the end of the book, it said, "Some new ideas are here needed." And so there I was. Some new ideas were needed. Okay, so I started to think of new ideas. Kid said to me, "Say, what's that bird? What's the name of it? Do you know the name of that bird?" I says, "I haven't the slightest idea." He said, "Well, it's a brown-throated thrush." He says, "Your father doesn't teach you anything." But my father had already taught me about the names of birds. We walked and he says, "That's a brown-throated thrush." He says, "Know what the name of that bird? It's a brown-throated thrush. In German, it's called a Flügelflögel. In Chinese, it's called a Ting-Long-Tong. In Japanese, a Tohatahara, and so on. And when you know all the names in every language of that bird, you know nothing, but absolutely nothing about the bird. And then we would go on and talk about the pecking and the feathers. So I had learned already that names don't constitute knowledge, it's the knowing the name of something. That's caused me a certain trouble since, because I refuse to learn the name of anything. So when someone comes in and says, "You got any explanation for the Fitz-Cronin experiment?" I says, what's that? He says, "You know, that the long-lived K meson disintegrates into 2 pies. Oh, yes, now I know. But I never know the names of things. What he forgot to tell me was that knowing the names of things is useful if you want to talk to somebody else." So you tell him what you're talking about. Best way to progress, I always think, maybe, is to try to be as conservative. That's what Wheeler always said. To try to be as conservative about the physical laws as possible in explaining the phenomena. And if you continuously fail, then you gradually realize you got to change something. But if you start out by saying, "Got to change something," there's so many ways of changing, and you don't know how it's most likely you don't have to change anything. Most of the time we succeed ultimately in explaining these damn things in terms of the known laws, but it's the cases that fail are the interesting ones.
We're exploring, we're trying to find out as much as we can about the world. People say to me, "Are you looking for the ultimate laws of physics?" No, I'm not. I'm just looking to find out more about the world. And if it turns out there is a simple ultimate law that explains everything, so be it. That would be very nice to discover. If it turns out it's like an onion with millions of layers and we're just sick and tired of looking at the layers, then that's the way it is. But whatever way it comes out, its nature is there, and she's going to come out the way she is. And therefore, when we go to investigate it, we shouldn't pre-decide what it is we're trying to do, except to find out more about it. And so altogether, I can't believe the special stories that have been made up about our relationship to the universe at large, because they seem to be too local, too provincial. The earth, he came to the earth. One of the aspects of God came to the earth, mind you. And look at what's out there. How can it isn't in proportion. It also, another thing, has to do with the question of how do you find out if something's true. And if you have all these theories of the different religions, have all different theories about the thing, then you begin to wonder. Once you start doubting, which I think to me is a very fundamental part of my soul, is to doubt and to ask. And when you doubt and ask, it gets a little harder to believe. I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong. I have approximate answers and possible beliefs and different degrees of certainty about different things, but I'm not absolutely sure of anything, and there are many things I don't know anything about. But I don't have to know an answer. I don't feel frightened by not knowing things, by being lost in the mysterious universe without having any purpose, which is the way it really is as far as I can tell, possibly. It doesn't frighten me.
You have have to learn. These are kind of disciplines in the field of science that you have to learn. That to know when you know and when you don't know, and what it is you know and what it is you don't know. And it's you got to be very careful not to confuse yourself.